Let's continue on with the model fitting exercise in the exponential distribution, first by just going back and stating what our first two approaches were. That we took a look at the probability density evaluated at specific points of interest and used that to come up with a potential value for the parameter. And then we looked at, well, just a modeling ratio, saying that we don't want to just fit at a specific point, but rather our interest was trying to preserve some sort of fall or increase, almost like a slope type of issue, as we went from one aspect of the probability density area to the other. Right. We're going to continue on with this theme here and look at a cumulative frequency approach and what that might provide to us, because we found in the modeling ratio and even in the PDF at a specific point situation that we were going to end up with sensitivity to the interval choice that we had, and that's what we want to do here is to remove our sensitivity to the interval choice. And we had looked at a delta x of 0.5 in an earthquake magnitude kind of example. So in proceeding down that path, let's go back and recall just what the cumulative frequency model was all about. That our symbol here was the capital F, and that was the probability that our value was less than or equal to some specific value of interest. Okay, for the exponential model, associated with our earthquake magnitude data, then remember we had fx of x was equal to beta e to the minus beta x minus x naught, where x naught was our shift value, and we had set that equal to 3.75, the center of our lowest bin. And we had found, as we looked around those other approaches, that our beta was approximately equal to 2. Right? That was from our discrete model approaches as we translated it on into then the exponential model. Right. So now let's take a look, though, at this cumulative function. And we're going to keep this in a generic form here initially. And we're going to evaluate from our lower limit up to a specific value, x, our argument, and we'll put a dummy value in here for you purists out there. And so now it's somewhat just a matter of integrating this all out, substituting things in, and we get our beta e to the minus beta x minus our shift value dx, and that's going to be equal to minus e to the minus beta x minus our shift value evaluated from x naught to x, and that's going to be 1 minus e to the minus beta x minus x naught, which is a nice, simple, elegant form that works out real nice. We still end up here with just one single parameter. It shows up only once, which makes us kind of feel good too. Right. So what we might do is take once again a whole nother set of approaches of asking, well, where do we care about the model? Where do we want it to be most effective at? And so often, again, that in civil engineering examples, that's out in the tails. So we might be looking at, well, what's the likelihood that our magnitude of earthquakes is larger than 7, which could be turned around and looked at 1 minus the probability on the other side, the complement event. And because of our interval choice, you could, in terms of our data, look at 6.5, right? Normally in continuous world, that those two numbers would be the same. So this is only because of our interval bound that I have turned it down to 6.5, right? And with what we have right up here, then we can substitute in, we'll have, of course, the 1 minus all of this, so 1 minus 1, and then plus the exponential term, so we'll have e to the minus beta raised to the 6.5 minus our shift value. And you could either use the 3.75 if we wanted to go to the a different shift value of 3.5. This is where you might want to do that, right? So now we've just changed this x naught here, instead of being the center of the lowest bin, to be the absolute lowest number that we have in our particular model. And that then becomes e to the minus 2 times 3, or equal to e minus 6, if we're choosing beta equal to 2, and note that turns out to be 0.0025. Really the same thing that we had before, but the question was, here I substituted in directly for the beta of choice, but what if we didn't want to guess at that value and see how it worked out, but rather let's go after it in a more kind of direct way. How could we go about doing that? And one of the ways you do that is with a technique that we're going to get into more detail when we get into the descriptive statistics section. So this is really a little bit of a preview of where we head in the modeling kind of world. But what we could do is plot our observed CDF on a probability scale. And the idea there is, if the assumed model is correct, then the results should appear as a straight line. And we'll have a different probability scale or probability graph paper for each and every different probability distribution that's out there. And so in the old days, when you had to go buy graph paper, then that meant you had to keep a stock of a whole bunch of different ones around, and you're going to plot your observed ones on these different kinds of scales. And so that does beg the question of, well, then how do you get the scale? And one way you do that is that you solve the CDF for x in terms of the CDF. That's not always a tractable type of thing, but that's one of the great things about the exponential distribution, is that one is. So let's go back and take a look at that. Our CDF for the exponential is 1 minus e to the minus beta x minus x naught. Right? And we can solve for this function in terms of x, and we get x is equal to x naught minus 1 over beta natural log of 1 minus f. Right? And notice that means that we have that x varies linearly with the natural log of 1 minus f. Right? Y equals mx plus b. There's your intercept value, right? Here's your independent value now that you plot, and here's your other ones. Now here's your sort of dependent one. You're just flipping things around. And notice that now beta is going to be equal to the slope of minus natural log of 1 minus f versus x. Because we can turn this all around here. Let's make this look like something that we're more used to seeing, that you would have beta times x minus x naught equals minus natural log of 1 minus f. Right, so there's your y equals your mx plus b. So, for now, one big gigantic summary, sort of a practical data and model fitting, and this will get carried on later, is that one approach is to assume a particular probability model, and that'll give you a functional form for your CDF, and that'll leave you one or more free parameters. So now you have to go decide how you're going to get those. So you plot the observed CDF values versus x on a probability scale. And that could be a paper that's got the probability scaled already, and so now you're just putting the numbers on there. So it's sort of like a semi-log kind of scale. Or you can do the translation yourself and convert your CDF values through that scale, and then you can just do a regular plot of y versus x. And then you're just looking for a linear fit to estimate your parameter. And you do that in the area of interest. If that's the body of the distribution, fine, you do it there. If it's in the tail of the distribution, then you go out there. And of course, the tails are oftentimes heavily influenced by outliers, so there's sensitivities that you have to kind of go through there. And you have to make some sort of judgment, of course, overall about the fit that you end up with. And that's, of course, a tricky little deal, and part of what we do later on in hypothesis testing is come up with ways to have better estimates of that fit, or in parameter estimation we have some other ways to talk about that. And again, it sort of comes out to, if you're tail fitting, you're concerned about the extremes, well then you're looking at unique phenomena, and those don't come around very much, and so you have different kinds of issues and concerns that you're trying to address, as opposed to if you're just looking more at the body of the distribution, or more of sort of the overall global kind of fitting, where you have a more homogeneous situation, and your approaches then might be kind of different as you go through there. And so that look ahead starts to look at method of moments, method of, or maximum likelihood method, and then, as I said, we get into some hypothesis testing kinds of issues to estimate parameters and try to look at goodness of fit, and then we'll get also into linear regression models. Before we leave that, though, I do want to summarize one last couple of aspects about the exponential model. And that is that, of course, one is that it's a single parameter model. If you have a shift value, that shift value is usually one that you're choosing. So there's your PDF and your CDF, of course. looks a little bit simpler. Right? Now, one thing we didn't derive, but you'll find, of course, published right directly in your textbook, and they'll give you some guidance as to deriving this, and that's the expected value, or the mean here, is equal to 1 over our parameter, which I've been using beta. They use lambda. It's just a parameter. It's no big deal there. The variance here of x then is equal to 1 over our parameter squared. It's kind of interesting because that means sigma is 1 over beta, and it automatically means here that the coefficient of variation is going to be equal to 1 over beta over 1 over, I should say 1 over beta over 1 over beta, sigma over mu. And that's equal to 1. So we automatically have 100% variation. And if our interest is in the body of the distribution, this may not be a very good model to use. But if it's out in the tails, well, then that tells us something else. Right? Another really important factor, we didn't derive this, but the book talks about it, and it's an important one to take a look at and convince yourself, and that is that this model has a memoryless feature to it. That telling me if I'm going to model this for, say, inter-arrival times of earthquakes, that I've had no earthquake in the last 20 years, and that doesn't influence what I think the likelihood is of having an earthquake in the next 20 years, is kind of a surprising result. It doesn't really match with physically how we think stress builds up on tectonic plates, and somehow that should, the activity or lack thereof in the last X number of years should influence our odds of having something in the future. Thing is that the exponential model doesn't have that, and yet we use it an awful lot, even in earthquake engineering, and partly because it has many other characteristics that are effective in modeling that particular kind of process. One of which is that it's easy to work with, it has a single parameter, and we can fit it locally to the data of interest in a much easier fashion than a lot of the other more sophisticated models. But as I said, it has this unfortunate part in that case, or property, that it does not have memory, and that doesn't jive with what we think is mechanically going on in the system. So there's always that feature about models, that they are not the real thing. They are idealized representations. And as such, we get something with some models, but we give something up usually. And if we want more resolution, we want a better fit, we then have to go out and get more data, or we have to deal sometimes with less easy to work with, less tractable sorts of models oftentimes.